Welcome to Lesson 34. Before we start, we're going to go ahead and go through a couple of examples that refer to materials from last week. So looking at single factor ANOVA. So we have two plots here, and based on the graphs, we want to know which graph implies that there's going to be more difference in favor of the alternative. So which graph is more likely to give us evidence that the means differ for at least two of the groups here. So looking here, the actual values of the means, they're pretty similar. It's going to be plot B. So it's not just the distance between the centers here. It's also going to be how spread out within each group we're looking at. So the more spread out the centers are, the more evidence we'll have. Also, the smaller the spread within each group, the more evidence we'll have. So looking here, we have results from an ANOVA table. So this is like a T for treatment. So from the ANOVA table, which value represents the average variability within the treatment groups? So if I'm looking at within the treatment here, I am looking for the mean square error. So like we mentioned last week, residuals and error we tend to use interchangeably here sometimes, and mean square, so I just need to line up. There we go. There we are there. And those are our examples. Okay, so here we are, lesson 34, inference for categorical variable. So what we've been looking at the last several weeks here, we've been looking at inference for a quantitative variable. So we've been looking at means specifically. This week, we're going to look at proportions. So we're going to talk a little bit about types of variables and look at proportions and describe the sampling distribution for p hat. So a categorical variable is numerically summarized using counts, percents, and or proportions. So I might say, hey, I have 20 students that I surveyed, too small of a sample probably. What proportion of those students say they agree with whatever statement? So you could look at the count out of 20, you could look at the proportion or the percent. So ultimately, our parameter here is going to be a population proportion. We use the letter P. This is one of the few instances we don't use a Greek letter most of the time. You might find a really old school stats book that does. The Greek letter we used to use was pi. However, that's confusing because in stats we use the value pi a lot. It got very confusing. So we're going to stick with the letter P. And so the letter P is going to denote the proportion of whatever population that has our variable of interest. So you might say, oh, are you right or left-handed? And maybe you're interested in the proportion of all students that are left-handed, something like that. So, yeah, looking at left-handed folks. The sample proportion, it's what we usually are more likely to have access to. It's going to be the proportion of the folks in our sample that have the characteristic of interest. I like to put into quotes successes in quotes because a lot of times our definition of success, what it means is, yes, the variable of interest is present. It does not mean like, yes, this is a good thing, because a lot of times we might look at the proportion of people that get sick or that die or that sort of thing, or that are defective. So it may not be successful in the traditional sense. It's more of successful in that characteristic is present. So however many people are left-handed out of my sample of 20 over the total sample size, which I'm making up as 20. So the scenario is very similar to the situation where we wanted to estimate a population mean. We're going to do that by taking a sample and finding the proportion in that sample. So you have a population of all U.S. adults, and you want to know the proportion of all U.S. adults that are left-handed. So your next step will be to take a random sample, from that random sample, we're going to find the proportion of adults that are left-handed in the sample, and then make a statement back. So cautions, if you don't do this step, you can't do this step. They're very, very important. They absolutely are very dependent there. One thing to note is you can think of a proportion. It is an average of ones and zeros. So if you assign 0 values to individuals that do not have the characteristic present and ones to the characteristic that's present, this is the average. Taking the proportion is equivalent to taking an average of those ones and zeros. So suppose I have 3 out of 5 in my sample, real small sample, are left-handed. I could think of this as p hat. I have person 1's left-handed, person 2, person 3, and then I have 2 people that don't. I'm going to just get 3 over 5. So that's one way to think about it. So now that we are taking a sample and looking at the sample proportion, we might want to talk about how the sample proportion is going to behave in the long run. So if I were to repeatedly take samples, what could I expect to happen? So on average, if I were to repeatedly take samples from the population and calculate this sample proportion from every sample, the average of all those p hats is going to be the true value of p, the proportion from the sample, which is good. This means that it's an unbiased estimate for the population proportion. The standard deviation of all those p hats, we know that it's going to be, well, you can denote it sigma p hat, and that's going to be equal to the square root of p times 1 minus p over n. So it's going to be very similar to us finding the sampling distribution of x bar, but now we're looking at the sampling distribution of p hat. So you start off with a population. You want to know the population proportion. So you go ahead and take a random sample. From that sample, calculate a p hat. Repeat, take another random sample, calculate another p hat, take another random sample, get another p hat. And you can keep going. You can keep taking random samples. You can keep calculating p hats. And then you take these p hats, you can go ahead plot them. And that distribution has a very, very specific shape. You can say, hey, it's centered here. On average, it's hitting our mark. The average is the true proportion. And we can talk about the spread here. It's that standard deviation of p hat. What's neat is the central limit theorem will kick in here as well. So the central limit theorem, it tells us that as long as our sample size is big enough, the sampling distribution of p hat, it's going to be roughly normal. It's going to be centered at p and have a standard deviation of that square root of p minus 1 minus p over root n, which is really great. The definition of if n is large enough does change up a little bit this week. It's not going to be, hey, rule of thumb, hey, 30 is great. We're going to have a slightly different rule here. So new thing here. So one of the examples we'll look at throughout here, we have a manufacturer. They go ahead, they make some paper coffee cups, and since they're in the manufacturing business, they want to kind of estimate, okay, well, how many, what proportion of all the cups that we make are defective? A lot of times, if you find that you have a proportion above a certain level, they'll stop the process, try and fix the machine, etc. So they go ahead, they take a large batch of cups, and they want to estimate the proportion of that entire large batch of cups that are defective. They take a random sample of 200 of those cups, and they find that 28 of those 200 cups are defective. We want to know what is the estimate for the proportion of defective cups. So, well, the proportion of all cups that are defective. So it wants to know our point estimate. So what we saw from the sample, the proportion we saw from the sample, well, we had 200 cups in our sample, and 28 of them were defective. This is what I talk about saying success, because the success here is being defective. So 28 of them were defective. And you can go ahead and simplify it to 0.14. So what this is saying is if I had to estimate what the proportion of all cups in this large batch that are defective, I would start here. I would start with what I saw in my sample. I saw about 14% in my sample were, exactly 14% in my sample were defective. That's where I would start. That would be my point estimate. So then, distributions and inference. This will be very similar to when we were looking at quantitative. So for the cup example, I happened to pull from a place where I knew that actually 12% in that entire population were defective, and the remaining 88% were not defective. So there's this population distribution. So it's the distribution of all collection of observations. So here it looks like we have proportion on the side. You could have counts, but it's the idea that if I had all observations in the population, I could put them into a bar plot. This is a bar plot, absolutely, because each cup, it's defective or it's not defective. It's one or the other. We're usually not lucky enough to know this distribution. We usually do not get to know what the population distribution will be. Then the sample distribution, so sampled, this is when you take a sample of 200 here from that population. So I took my sample from the population. P hat is going to be what I observed. I observed 14% of the cups in my sample of 200 were defective. So this sampled distribution is not unique. It can change from sample to sample. If I took another sample of 200, this distribution could change. If I took another sample of 200, that distribution could change. The sample distribution usually is the only distribution we're lucky enough to actually observe. So we usually aren't fortunate enough to have all the population information. Information from a sample? Yes. So this is just one sample. So then the sampling distribution of p hat, before we were looking at the sampling distribution of x bar, that is if I took every single sample of, unique sample of 200 I possibly could, and calculated the sample proportion in each one of those unique samples of 200. If I go ahead and I took the average of all the sample proportions there, I'm sorry, I hope I'm not saying sample means in here, get 0.12, which should match the population distribution, and then I get a spread for how spread out, like from sample to sample, how much can I expect the sample proportion to vary from sample to sample. And so this is generally, it's a theoretical distribution that if we were to repeatedly sample, we could know, like, from if I had sample 1 of 200, get a p hat of 0.14, take a second sample of 200, get a p hat of 0.15, keep going on and on and on forever, I can know how much from sample to sample that p hat will vary. So that was lesson 34. We're going to get into doing a confidence interval for a proportion next, as well as calculating sample size.